So now we will talk about a very interesting data structure, and this is called heaps. And they are also known with priority queue abstract data type. So let's try to understand what are heaps. What do I mean by a priority queue abstract data type? So heaps are again binary trees. Okay, so that would take us back to binary trees, but there is some advantage in terms of implementation that we will see. So let me define a heap. So a heap is a binary tree with the following property. So now we said all the interesting things of a binary tree generally come with certain restrictions. So now we are talking about what are the restrictions you put to a binary tree so that it becomes a heap. So there are actually two restrictions. One are based on the structure restriction, and second is based on the value restriction. So in terms of a structure, so it is a not complete, it's an almost complete binary tree. So remember this definition of almost complete binary tree. So what would happen? You start filling it from top to bottom and left to right. So what would happen? So those all the levels, but last must be completely full. And in the last level, all nodes will appear to the left. In the last level, all nodes must appear to the left of the empty positions. So there cannot be an empty position in between. So something like, yes, you're keeping on filling it, but suppose this label 0 is full, label 1 is full, but at label 2 you have only one node, this is fine. And this node has to be here. So I cannot put it at this position or this position or this position. Because all the nodes in the last label are to the left of all the empty positions. So there are 3 empty positions. 3 empty positions. Okay, and it is filled from top to bottom. So these are full. Okay, so this is the structure property. Fine, structure is fine, that is all right, but what is the restriction on the values the nodes can contain? So the value restriction is that so this is mainly between a node and its parent. So between a node and its parent, what should be the connection between the values of each? Okay, so the connection still holds the node, parent, left child, right child, that still holds. So for any node U and its parent P, so value of P would be greater than equal to value of U. And this is for a max heap. So immediately that means, so when you talk about heap, you can say max heap or min heap analogously. So value of P, and generally if I don't say anything, I'm just talking about max heap by heap. So value of P is greater than equal to parent is greater than equal to value of the node. So Sorry, I was just verifying that my mic is working. Yeah. So now, so value of t has to be greater than equal to value of u, and so for any node, the value is, and if you try to extend it, that means it's larger than any value stored in the subtree, because its value is larger than its child nodes. So that means it is, and their child node have a value larger than their child nodes, and so on. So any node, so this that means this node will have the highest value among this, right? And similarly for this subtree, this node will have the highest, and so on. So you can see for any subtree, the root will have the highest value. All. So, and similarly for min heap. Okay. So now we understand the structure property, the AJ value property. And they're not very difficult. Almost complete binary tree. Yes. And value of parent is always getting equal to value of its children. And that happens throughout the tree. So let's take an example. So, so parent having the highest, and the two children, let's say, and on suppose only 50 has two children, and they are filled from left to right. And 25 does not have any child. And labels are 0, 1, and 2, and 0 and 1 are full, but 2 is not full. But whenever it is not full, children nodes are from left to right. Okay. So I can make some simple generalization. For example, if I have a heap of maximum label L, so that will contain, so at the 0th label, 2 to the power 0, first label 2 to the power 1, up to 2 to the power L minus 1 nodes at previous levels. By that I mean 0 to L minus 1 levels. Okay. And at level L, it will have between, so it will have at least one node at level L, because you are saying the maximum level is L. So it will have between 1 to 2 to the power L nodes at level L. Fine, I think that is trivial. Now, once I understand this property that nodes are filled from top to bottom, left to right, and can I use a simple representation for heaps? How can I, do I still have to go to tree and using all those pointers, or can I use a simpler representation for heaps? So it turns out, because they are filled from top to bottom, right, and left to right, so you can actually use simply an array to represent a heap. Okay. So because of this property, and we will just explain this why. So because of this property, so I can represent heaps using an array. And what do I mean by putting that? And so I fill them from top to bottom. So filling it using nodes from top to bottom. And at each label, left to right. Left to right at each label. Okay, so I can easily say that that means the in the array root is the first node, and then I have two nodes or two elements for the next label, and similarly four elements for next label and so on. Now in array you will start from 0, but here I'm just taking convention. So let's say in array I start from 1. So I have to fill n elements. I have to fill n elements from 1 to n positions in the array. So, so go back to your previous heap. How will you fill it? 100, 50, 25, 30, 20. 30, 20. And yeah, you can still use the notation even say a 0, you don't put anything. So index 0, you don't put anything. From index 1, you keep on putting. So 1 to 5 in this case, so that is up to you. Now, why did we say that this is very convenient? You see, you know where is your root. Root is at index 1. So A1 is your root. And you can easily go from, see, what is the main thing that you do in a binary tree? You need to have an easy way to go from your parent to child and child to parent. Now, can you find a simple rule by which you can move from parent to child? So actually, if you think about, think about a node at index I. Okay, so where will the left and right children be located? For this node I. So you can go back and check. So here this was 1, 2, index 2. Where were the children? 3, 4, 5. And similarly for index 1, they were at 2 and 3. So actually it turns out for any node I, the left child will be at index 2i and right child will be at index 2i plus 1. And uh, that looks quite easy. That looks quite easy to traverse from a node to its children. No, why does that happen? Why does that happen? So the idea is very easy. So idea is very easy. So I have, so you see, I have label 0, then label 1, label 2, and they are full, right? Each level is full, and so on. So what would happen? Because I'm starting from 1, so first node will start at 1. And here, first node will start at 2, then start at 4, it will start at 8, right? So the child of this node is twice, and the next one is 3. 2i plus 2i plus 2i and 2i plus 1, 2i and 2i plus 1. And if you take any other node like this one, what would happen? For this, the child are anyway 2i and 2i plus 1. And if it node occurs at some position after this, for any node, they are having two children. So you are anyway incrementing 2. You are, uh, so if there are some few nodes, you are putting two children before. So that becomes very easy then. So at any node I, index I, your children located at 2i and 2i plus 1. Similarly, can I say about the parent? Parent for a node at index I. And now you can just backtrack from here. So for 2i and 2i plus 1, it is at I. So for index I, it will be I by 2 floor. Okay. So yeah, that will take care of both I by 2 floor. So this is very easy. Now I don't have to go to pointers. I can simply traverse my array indices and go to my children and my parent. Very nice. So good. So that what we saw heap property and we saw I can represent using arrays. Right. So now, what are the operations I will can do? Now, while I will talk about operation now, because we have understood ADTs, let me go and talk in terms of ADTs. So I said heaps are also called priority queue data structures, abstract data type. So what is a priority queue abstract data type? Does the name say anything? So, so priority queue, you can think of it as if, so you are receiving some jobs and each job comes with a priority. Okay, so maybe you all are, let's say, running your codeness server and you have some priority that may be given by you or given by someone else. But each job comes with a priority tag. And what you have, your task is you want to maintain a queue for these items, but you want to process as per the priority. So you will want to remove removal according to priority. So something like the item that has the highest priority should be executed first. And you remove that. And then you take the one with the next highest priority. So removal according to priority is very important. And the jobs will keep on coming. And every time the jobs come, so jobs may come at a given time together, or it may come at certain times, intervals. And each time they'll come with the priority, but you want to always find the job with the highest priority. So you want to find jobs with the maximum priority. So immediately once I say that, you can think about what are the operations do I need. So yes, what are the operations? I have a list of items and I want to find the maximum of these. So first is find max. So that is return the maximum value in the list. Then the next would be, okay, you're finding that element, you also have to remove it and maintain the data structure again. So you want to do delete max. That is return the max value and say delete that. Okay. And deleting is more important. Return is not, you may or may not do return, but so I'll just put that in bracket. So delete the maximum value. And when you delete the maximum, you have to maintain the data structure. What is the operation you can think of? So you see, you may have new jobs coming in. So you also have to take care of insert. So whenever you have to insert a new job, and what we will do. And so so by the way, yeah, these three are the main operation for priority queue data structure. Now, before I talk about heap, you will say, okay, why can't I do that with some of the data structures or simple data structure we have talked about? So for example, Why can't I just do that? So uh, let's say I have this find max, I have delete max, and I have insert. So why can't I do it with the simple things like a simple unsorted array? Or let's say I maintain a sorted array. What I will say, no, we will use heaps. Let's see what happens in heaps. Okay. So if I use unsorted array, find max, what is the complexity of find max? Set of elements, find the max. You see, I have to traverse the whole array to find it. So this is order n, bad. In sorted array, it's easy. Find max, max element is always, so if it is from in an increasing order, then it will be at the end. So this is order one. I know the index. Delete max. So in unsorted array, if you delete an element, uh, delete an element in unsorted array might need you again order and thing. You will delete an element, then you have to shift everything. So this will be, or if you don't want to shift, of course, you can do it in order one. Let's say this is order one. Because you don't know how many insert delete you will have to do. So yeah, you will have to shift for sure. What about sorted array? In sorted array, if you delete in max element, see that is easy because you don't have to shift. This is the last element you're deleting. You can just say, okay, now my size is one less. So this is again order one, and it looks like, oh, why don't you go for sorted arrays? Right? Both these operations are order one. But then comes the pain point insert. So you may have any job with any priority value. So what is the insert complexity in unsorted array? Order n? No, it's you can see because unsorted you can just put it at the end, right? So this will be simply order one for an unsorted array, but in sorted array you have to put in a correct position. Yes, and you have to shift the element. So this will be the pain point order. So yeah, so there was one thing where unsorted array was good, but sorted array was not very good. And insert you see can happen for say all the elements, and you see the complexity will go square and square if they are like order n elements to insert. I don't want that. I want at most log n. So by heap, I am talking about a data structure where you will do find max in order one. Remember, max is always the root. Just delete max. We will see this you can do in order log n. And insert again, we will see you can do in order log. So yes, so delete max takes more time than sorted array, but just log in. And insert helps a lot. So heaps help a lot with insert. This happens a lot. So that is where we will talk about heaps. So that gives you some efficient data structure for doing these three operations. Plus, we will also talk about the operation of build heap. So where the idea is that, see, one thing is you insert an element in by n, but second is you are already given an elements. You're given an elements and you want to put them into heap. Want to create a heap. So can you do better than? Can you do better than order and log? And we will see we can. So these are the four operations we'll talk about. So I don't think I need to talk about find max. Find max is simply return A1. So find max in heap is just A1, right? Constant enumeration. Let's talk about others like insert and delete max. So there is one thing. So for both insert and delete max, the way I proceed is as follows. You see, when I do insert, I don't know where to insert such that my heap property is maintained. And my heap property has two things, the structure and the value. Both have to be maintained. So what I do, I first ensure structure property. So I ensure that my structure property is maintained. And then I ensure the value property. And if I do that systematically, I will be able to do these operations in order logging. So let's see some examples. So let's see for instance. So suppose I have this heap. So this is the same example that I took earlier. And I want to insert 200. Okay. And this would be a simple function like insert. I need to give the array heap. I need to give the size, say n, and I need to give the new value I want to insert. That would be a simple function. So you see, now I'm doing insert. So go back to our rule. First ensure structure property, then ensure value property. So now you tell me where should I put 200 in this heap to ensure structure property? I cannot put it on any of the above labels. You see, they are already full. And I have only this label free. And if this is also full, I have to keep it in the next label. So now this has empty. I should mention structure property. So I will put 200 here. So let me use, so put 200. Fine, done. Structure properties ensured. Now go to the second step. Ensure the value property. And you see now value property is not holding. So we wanted for every node, its parent's value is higher than that. But you see it is not happening. So parent is 25 and this is 200. So I need to do something to ensure the value property. And what will I have to do? I will just have to compare with the parent. And if the value property is not holding, I have to swap this. Right? This is all I have to do. So now I want to percolate the value up. Very important, I have to only percolate it up. I don't have to go down. So what you will do, swap this value with the parent if heap property is violated. Okay, and so what you will do, you will change it to 100. See, this remains same. 30, 20. Percolate up. So now what will happen? 200 will come up and 25 will go down. So this is fine. But now again, you will see this is violated. So you will have to recursively do that until you reach root. That's all. So violated. Now continue this until the heap property is restored or you reach the root or the new value reaches the root. Now, what is the time complexity? You see, what is the height? What is the height of a heap? Heap is a almost complete binary tree, right? So this is time complexity is nothing but the height of the tree. I have to go from a node up to the root. And because it's almost complete, so I know that for L levels, there are greater than equal to 2 to the power L children. Yes. So yeah, so this height is, so that means for n nodes, the height is at least log n. Height is exactly log n. Height is exactly log n. So for n nodes. So that means time complexity is nothing but order log n. And this is all good. So I can do insert in order log n thing. So what will I do next? So from here I will now swap 200 and 100. So this will give me 200, 100, And sorry, if you go to the left, 25, 50, 40, 20, and you verify. Nothing happens to the left sub-tree of 200, but yeah, right one has changed, but the heap property is good. So this is now a heap. Okay. So fine, this was your insert operation in log, only log n time. Now what happens with the delete max operation? So I have to delete the root, okay, and I have to restore, restore again. So how do I do that? How do I do that? So remember again the rule. First, maintain structure, and then maintain the value property. So let's say, suppose this was my heap, and I want to delete 200. I want to delete 200. What will I do? So then you would delete max. So to delete, so 200 will no more be there. So what will happen? 200 will no more be there, and the size will decrease by 1. Yes. But then you see your structure is not maintained. Now you don't have a structure at all. The structure is gone. Your uh, top label is empty, and that is completely unacceptable, right? So what you will do to maintain your structure? What is the minimum thing you should do? And what we do actually here is that you take the last element and copy it to the root. Okay. So element at the root is the max value stored in the heap. So we delete it by copying the last element into the root. The last element of the array to the root, and then decrementing the size by 1. And decrementing the size by 1. And you can ensure that yes, it maintains the structure property. You have taken the last element, put it to the root. Now all the labels are full, and last label is full from left to right because only the last element is gone. Okay, it has gone to the root. But now you see what will happen now. So you have now put 25, 50, 100, 30, 20. That is your root. That is your heap, sorry. And it is a good in structure. But what would happen next? The next step was maintain the value property. So you see immediately it is not maintaining the value property. 25 should have been the largest. So here, but it is less than 50 and less than 100, right? So it is not maintaining the value. So what would happen? So when you place the last element at the root, so placement at the root may violate the heap property, the value restriction. So what you should do then? So how you can restore your heap property? And you see in the case of insertion, I started from putting it at the end and went up. In the case of delete max, I have now put the thing at the top root, and now I have to go down. So I have to compare it with the children, and with whom should I swap? So I have two children here, 1500. Can I swap with 50? See, that will be fine, 50, 25, but 1500 will not be fine again. So it's best if I find out among the two children which one is having the maximum value and swap this with that child. Okay. And I keep on doing that until my property is restored. So in that case, we swap this value with the child having a larger value. And you continue this until the heap properties restored. Or you reach to a leaf node that does not have any child until the heap properties restored. Or you reach a leaf. Okay. Now, what is the complexity? You have to at most go so in this case, what you will do 50 and 100. The maximum is 100, so you will swap it with 100. So you will take it to 100, 50, 30, 20, and 25. And that's all. You don't have to go any further. So because 25 does not have any child, you stop here. So you will have to go from the root at most to one of the leaf, right? So this complexity is again just log n. That's for the height. So this is again order log n complexity. So very good. So now we had the three things. So we learned find max is order 1, delete max is order log n, insert is order. So now let's talk about the fourth operation, that is how do you build a heap if you are given n elements. So what about the build heap operation? So again, you see if the elements are coming one by one. So if elements come one by one, you have to do insert one by one, right? You have to insert one by one, and that would be asymptotically n log n, right? So that would be n log n. You can't do anything there. But if all the elements are present together in an array, but if all elements present together in an array, it turns out that we can do better. So how do we do that? And the idea is that we go bottom. So let's see, let's take an example. Let's take a simple example. Suppose I have just 5 elements, 20, 25. So I'm taking the same 5 elements, 30, 50, 100, and let's say they are occurring in a sorted manner, right? And you put them in a heap like this. So you start by assuming this is a heap. So your heap will be 20, 25, 30, 50, 100. It actually turns out to be a min heap, right? So yeah, it turns out to be a min heap, but I want a max heap. I want a max heap. So this is not a max heap. For sure. And now I have to convert it to a max heap. So what will I do? So what is the idea? So idea is that here you go bottom up. Start ensuring that things below you are always already heaps, and now you are making sure this current node to be heap. So for example, is 50 this subtree heap? Yes, single node is heap, 100 is heap, 30 is heap, right? Individual they are heap. So So I can say that, so the leaf nodes, now can I also give the location of leaf nodes if there are n elements, so a1 to an. So what would be the location of the leaf nodes? You see, for the last node n, the parent is n by 2. Yes. So that means this is the last node who is a parent. So starting from n by 2 floor plus 1 to n, they are all leaf nodes and they are already heap. Now what I do, I now go back, I start from n by 2, go up to 1 and keep on ensuring that the sub-tree rooted of that node is heap. So what I do, so from n by 2 to 1, so I start going one by one, ensure that the subtree rooted at node I is a heap. Okay, and if I can do that starting from n by 2 to 1, I am done. So because if my root is complete heap, that's all I need. That's all I need. But you can say, okay, why don't you just do for one? So the idea is that you make use of the fact that its children are already heaps. So the main fact that you use for any node when you're going, its children are already heap. So, so that is when you're going at node, when you are at node I, the two subtrees, they are both heaps. But now after including I, you have to maintain the heap property. And that you ensure by going from, so n by 2. So for I is equal to n by 2, I greater than 0, because I have to go up to I is equal to 1 and decrement I. Yes. And ensure that there's a heap, you heapify at that point. So you can say max heapify h and size and at location. And this is how it looks like. So you are at node I, and the two things are already heaped, the left and right sub. So how will you do that? How will you do that? How will you heapify at node I? And you will say, okay, this looks very similar to what is something I have already done. So this max heapify is analogous to, what was the operation? Yes, delete max. Delete max. Delete max, what happened? You put something at the root from the end, and the two things were already heaps. Yes, this was a heap, and this was a heap. And you put something to the heap. And what you did, you just swap it with one of the child, whichever is the larger. And you will do exactly the same for this max heapify. So, so what you will do, find the max stored, max value stored in the children. That is 2i and 2i plus 1, and compare with AI. Yes, and if AI is smaller than the max, you swap with max. And you call it and call this recursive. So that's all. So what you will do, at node I, it may not be following heap property, but they are heaps. So compare the max value, whichever is max. If this is smaller, you swap and keep on doing that until you come down to the leaf. So Keep on doing that. So, and you do that for all the nodes. So let me go back to my example. So this was my heap. So 20, 25, 30, 50, 100. Now this, and this are already heaps. Let's go for 25. So I want to heapify at that node. So heapify at 25. So what he will do, he will compare 25 with the children. Maximum is 100, right? So you put 100 here and this particular thing is a heap now. That's all. You don't have to worry about what is above. So you go 20, 100, 50, 25, and 30. Okay. Now again you go back. Now the only node left is 20. So 20 again, this is a heap, this is a heap. Compare the max, max is 100. 100 is larger than 20, you swap. So from there we go to 100, 20, 30, 50, 25. Again 20, you compare with the two. So max is 50. So you swap. So this gives you 100, 50, 20, 25. And you are at the leaf. So this is now a max heap. So just by calling max heapify, starting from the node n by 2, in this case n is 5, n by 2 is 2, up to 1. You were able to achieve, you were able to get it. So by the way, if you compare with what was the initial heap, it's not unique. So given the set of integers, heap is not unique. You can create multiple heaps out of it. So for example, I can swap 30 and 50, right? Perfectly fine. This is still will be a heap. Okay, very nice. So this looks very simple again. For I is equal to n by 2 uh, up to 1, you just max CP5 at I. Okay, and this max CP5 was similar to the delete max operation. The same thing I was doing. So now what is the time complexity? What is the time complexity? If you look loosely, you will say, okay, I am doing from n by 2 up to 1. I am calling some maxify, and that is similar to delete max. So this is as if I'm doing delete max n by 2 times, and that will be n by 2 log n. This is n log n. So what is something, what is interesting here? I could have inserted n elements one by one. Right. So now, so actually, yeah, this is a loose way of seeing. I can actually put a very nice font. So now this is not the correct way. So let's try to find the time. So, so there are n nodes, and let us say the max. So maximum label is n. See what we are making use of here. So when you are heapifying, you see when you are heapifying here at this label, you are not going up to the root. You are at most going from this label up to the leaf, right? And similarly, when you are at this label, suppose this was not the root, you will go from here up to the leaf. So why do you need to count from the path from root to leaf every time? You can just count from the label to the leaf. And can you give a better, can just give a better bound? Okay. So let's say L is the maximum label, and I can say the n is between 2 to the power L less than equal to n less than equal to 2 to the power L plus 1 minus 1. Right. So because at the last label there will be at least one node, and there are at most 2 to the power L nodes. So that is the relation I can say between the label max label and the number of nodes. Now at a given label k, There are 2 to the power k nodes. At most, if it is not the final one, at most 2 to the power k nodes. Okay, so I can, okay, fine, sure. No. So now let's count how many times we are doing heapify. So, so when I do a heapify, on a node at label k, how much time does it take? So you are at label k and you have to go up to label L. So you will anyway go down. So this will take order L minus k time. If you are at label k, if you are doing heapify for a node at label k, it will take order L minus k time, right? Now you have to go from label L minus 1 up. Label L, there are all leaf nodes. You don't have to worry about label L. So let's say I try to count all nodes from k is equal to 0 to L minus 1. Okay. So I do at most L minus k operations for each of the node. And how many nodes are there at label k? At label k, there are 2 to the power k nodes. Mhm. So time complexity for heapify is less than equal to this. Okay. Now, how do I simplify this? So you see, we found some connection between M and 2L. I can try to use that here. So if I put it here, so 2 to the power k is less than equal to n by 2 to the power L minus k. Right? So this I can write as less than equal to n sigma k is equal to 0 to L minus 1 L minus k by 2 to the power L minus k. Now, okay. So let's say take this quantity. So n times k is equal to 0 to L minus 1 L minus k divided by 2 to the power L minus k. Now k goes from 0 to L minus 1, right? So I can try substitute, let's say h is L minus k. So then this will be so L minus k is h, 2 to the power h, yes, and n is here, sigma. Now, uh, when k is equal to 0, h becomes L, and when k is equal to L minus 1, h becomes 1. So h becomes from 1 to L, right? Okay, fine. Now this thing you must have seen quite a few times. Okay, so what is this? Uh, so this is less than equal to the infinite series, less than equal to n times sigma h is equal to 1 to infinite h by 2 to the power h. Now this is what? This thing. So this is 1 by 2 plus 2 by 2 square plus 3 by 2 cube plus so on. So let's say this is S, right? And how do you find this value? Just take a shifted version, divide by 2, because infinite series 2 square plus 2 by 2 cube. And then you subtract. So S by 2 is 1 by 2 plus 1 by 2 square, infinite series. And that you know is 1 by 2 divide by 1 minus 1 by 2. and that is 1. So S has a value of 2. So sort of works. S has a value of 2. So this is equal to 2n. Okay. So that means the complexity of P5 is nothing but order n. So EP5 or not EP5 is actually the build heap. The build heap is of complexity order n, and that is very interesting. So that means if you give me elements, n elements, I can create a heap in O(n) time. Wow, O(n) time, and that means I don't have to even worry about using L log n time to create a heap. So that is interesting. So now, we have talked about all the main operations. We have talked about uh, doing insert, doing delete max, find max, of course, and build heap. And they are quite good. This is order login, order login, order one, order. So now just like for AVL, you could do sorting. Can you also do a sorting with heap? Can you also think about heap sort? Because given n elements, you can convert into heap in order n time, right? So that is as if feeding the elements. So can you do something with heap to sort them? Looks easy, right? So what you should do? So in heap, the maximum element comes at the top. So you can just keep on doing delete max again and again. So first we build heap from the array. And then we keep on deleting the max element. Then we keep on deleting the max element from the array. And delete means you will output it somewhere from the array. And you see, if you want to actually do it in place, you can also put it in the place from which the element was taken. And storing this element in the vacant host created at the end of the current heap. So you don't even have to use another array. So you just, because remember what you used to do? So you used to, so when you're doing delete max, I'll take this element and put it here. So this is the backend post. So why don't you just swap it? So you just put it back here and keep on doing this. Okay, so you're just swapping these two. So what would be the complexity? This is easy. So heap sort. So you have make heap that will take order and time. And you do delete max. That is order log n for a heap of size n. So this you will have to do from m is equal to 1 to n. So over complexity is n plus sigma m is equal to 1 to n log n. Okay. And that is what? M plus log n factorial. Right? Log 1, log 2, log 3. All you adding, that is nothing but log n factorial. N factorial we just found out a few days ago, right? But can I say less than equal to? So this is less than equal to. So each of these is less than equal to. So this is n factorial. So n plus log n to the power n. So So this is order and log. So this is ordered and log n. And from what we did a few days ago, you can actually prove this is omega and log n. So this is actually theta and log n. This is actually theta and log n. Because you can always say this is greater than equal to log n by 2 to the power n by 2 to the power n by 2, right? And then you can prove this is omega and log n. So that means your Heap-sort gives you a theta and log n complexity. Again, it's more on a comparison based algorithm. It does a few more things, but yeah, again, does comparisons between node and its children and so on. But finally, it gives you a theta and log n algorithm. So you have another algorithm in your pocket that is n log n, use Heap-sort. Right. So in the course we found out two interesting things. AVL sort can give you n log n, and Heap-sort can give you n log n. And now the codes are pretty straightforward, so I don't have to give you the pseudocodes for these. And what I would suggest, so these are very simple codes, and you practice this. So for example, you practice this insert heap for a heap size and a new value. Try to write this code. Similarly, try to write the code for heapify. Heap n at a location n. And that will be similar to the delete max. Okay. And once you understand for this max heap, you can analogous kind of a min heap. So find this ends this very interesting data structure about heaps. I'll try to give some more interesting problems during the discussion hour. But yeah, if you have any questions, you can ask during the comments and my email. Okay then.